So welcome everyone. Our last speaker, and I think the youngest one, correct me if I mistake, is Małgorzata Flis. We'll talk about Lie group symmetries of differential equations and applications. Małgorzata, the floor is yours.
Thank you so much for having me. So yeah, as you said, Lie group symmetries of differential equations and application is the topic of my Bachelor of Physics in the field of physics, which is supervised by Dr. Javier de Lucas. And now I give you a quick outline of my presentation. So first up, I would like to give you a brief summary, then lay the foundations and move on to jet spaces, the main interest, which is the symmetry groups, and prolongation, which is later illustrated by the very simple physical example, the heat equation. So if we have a geometric description of a differential equation, we can speak about the Lie symmetries. So a sort of invariance of the differential equations under the certain group actions. And my work is aimed at students that are undergraduate and wants to use this formalism, which is described in my thesis, to use in the physically important differential equations of their choice. So for the start, as I said, some basic definitions. A local group of transformations, which is later on stated to be a Lie symmetry in certain circumstances. In general, it's an action of a Lie group on some manifold with properties that it's transitive identity if taken under the zero element, and then from those first two we obtain the third one with the definition of an inverse. And with the this definition really resembles the flow of a vector field. So having a group action, we can actually speak about an infinitesimal generator of such group action. And this would be a comfortable transition in the later part. So first, very simple example would be a group action given by the Lorentz transformation on the space of four vectors that transform under it. And the connection between the group action and the vector field, which is the generator of this group action, give us the well-known boost generator by the very simple computation. So another important and vital structure is a Lie algebra. So having a Lie group, it's a space of all right invariant vector fields on G. And since many of those structures that are applied in my thesis are only locally defined, we have a corresponding local Lie algebra and the of a local Lie group, which is defined in the neighborhood of the neutral element. So there's correspondence between the Lie algebra and the Lie group within the exponential map of it. And this also gives us later on the correspondence between the, actually via the morphism, between the vector fields on some manifold M and the Lie group action of on that manifold of a Lie group G, and that will give us a tool to gain the symmetries of differential equations. So a very simple computation also here, just to illustrate my my thought before. If we have a Lie group, for example, a group of rotation, we can compose two elements of it and obtain the generator. So the Lie algebra is here given by only one vector, a generator of rotations, and the exponential map transforms it back to the rotational matrix. So if we want to geometrically describe the differential equations, we need to have the space of variables which are dependent, independent, and also derivatives of them, since it's a differential equation. And the jet space, shortly speaking, is such a prolonged space. The set of variables on the jet space is given by defining the relation between the sections of a certain bundle over the manifold of those variables. And those sections are said to be k-equivalent if they're, let's say, the Taylor polynomial is exactly the same at some point to the certain order of the equation, and this class of equivalence is a jet, and the disjoint sum of those jets over the points on the manifold is the whole jet space. It is indeed a manifold, and having some action on that manifold, we can say when this action is a Lie group symmetry. So prolongation of such action would enable us to act not only on the dependent and independent variables, but on the jet space, on a subset of a jet space. The subset of a jet space, which is a solution, is invariant if this is a symmetry group of this set. So we can speak about corresponding infinitesimal criterion of that. So having a prolonged group action, we can say that it's infinitesimal generator, which is a prolonged vector field, acting on the zero level set of a function that admits this differential equation gives us zero. So this is a criterion that must be satisfied for G to be a symmetry group of a system. And uh, simply speaking, the prolonged vector field is the same with additional coefficients within those variables that are the derivative variables. And these coefficients it can be proven that they're given by such expression. So just in terms of the coefficients of the not prolonged vector field, when the capital D is a so-called total derivative, so a partial derivative of an order up to the order of the equation. So a very simple illustration of all that I've said before would be a one-dimensional case of the heat equation. This is second order differential equation, so it's described in the second order jet space and given by the zero level function delta, and the infinitesimal generator of symmetries, we assume there are some symmetries, is of a basic form as written here as X. The prolonged one is the same with additional coefficients, as I said. We obtain those coefficients by the prolongation formula given before, and this is very general form up to this point when we use the infinitesimal criterion. Infinitesimal criterion distinguishes the submanifold we are interested in the jet space. So obtaining those defining equations, they are partial differential equations for the coefficients of the not prolonged vector field, are usually pretty simple to compute, but there are a lot of them, and yeah, it can get complicated, but in this case, it is fairly simple, and we obtain the coefficients for the not prolonged vector field and the correspondence between this Lie algebra and the Lie group action acting on this manifold lead us to this symmetry. So the first two ones, as you can obviously see, are the time and space translation. Third one and alpha one are the admit that this equation is linear. The fifth one is a boost, but not relativistic, like a Galilean, let's say, boost. And the fourth one is a scaling symmetry, while the sixth one is less trivial, but we can obtain a fundamental solution out of it. So to conclude Lie symmetries, let us dive into the structure of differential equations and check their invariance and possible directions to take after completing this thesis is to generalize it to the theory of Lie groupoids. So here are my sources, and thank you for the attention.
Thank you very much. It was a very interesting talk. And are there any questions? Well, if not, could you go back to this criterion you talked about?
Yeah. This one or those are, yeah.
Could you provide any like geometric intuition behind this?
Yeah. So in this case, when you have a differential equation, when you have differential equations, the solution can be written as some pairs of the argument and the solution. So this would be the solution would be associated with its graph, let's say, very, very simply. And we can prolong the solution to be rewritten as also all the derivatives of it. So this is a submanifold of the jet space. And if we prolong the action of the group, which only acts on if not prolonged, only acts on those not derivative variables, but if prolonged, acts on all of them, is also a solution. So actually, we are in the same submanifold. This is a subvariant, invariant subset of this. Yeah, this is a symmetry group then.
Okay. And one more question. I mean, as far as I understood, so you can get new solutions, right?
Yeah, exactly. As we could see in this um, in this example, just by the form of the symmetry. So the symmetries indicate, maybe let's call them the families of the solutions.
Yeah,
So so we
So
can create sort of new solutions within the families.
yes, and is there any characterization of the solutions you can get this way? I mean, you can get all the solutions, you can get some particular class of the solutions, or yeah, is it anything like this?
Well, I don't know if I understand the question correctly, or if my knowledge is enough to answer this question, because here you can see that one of, maybe I did not state that enough, 6 of those vector fields form the Lie algebra, actually. And this alpha one, the last one, is a infinitely dimensional subalgebra, because alpha is a arbitrary solution. So actually, it's more to it. I don't really know how to.
Okay, so the question is, in your setting, like you have these symmetries, can you get like all solutions of the heat equation?
Yeah, like, I guess so.
Okay.
Yes, sorry, maybe I'm.
Okay, thank you. Are there any questions? Any remarks? Okay, if not, thank you very much once again.